Another exam walkthrough for you. Here we have the first question where it says, let's go it up, that we have to tell the ionizing power and penetration of gamma radiation. So gamma radiation is having no mass and no charge. Because of no charge, it doesn't ionize, so low ionizing power, and because of low mass, it's highly penetrating. So your answer is going to be B. Next question. Fusion reactions are the primary energy source of stars. Which of the following gives the necessary conditions for fusion? So we know we need high temperature so we can have high kinetic energy to overcome the electrostatic forces. And then we need high density to have high collision rate to maintain the high kinetic energy. And along with that, we have high successive collisions as well. So we need high density and high temperature. Which of the following statements is correct about nuclear binding energy? So these all statements are about nuclear binding energy per nucleon, and then they're telling us with respect to the proton number. So as the proton number increases, the nuclear binding energy decreases. As the proton number increases, nuclear binding energy decreases. And then it says, no, this is wrong because nuclear binding energy per nucleon for all of these are different. Right, for all the elements with different number of protons is different. So this is wrong. Then nuclear binding energy per nucleon increases with proton number and decreases with proton number. We know this is not true. The reason being, we know a graph of nucleon number, which is basically the number of proton plus the number of neutron, and binding energy per nucleon. And the graph kind of goes like this. And if you see, the number of protons are increasing if you go this way. So it increases and then decreases. So you cannot say it always just increases. Nuclear binding energy per nucleon increases because proton number is increasing. That is true, but first it will increase and then decrease. So the correct answer should actually be D, because it's increasing, reaching maximum and then decreasing. The rest of the stuff is correct, but if we have the full picture, then D is the correct answer. And the full picture is this graph, very important. This curve is extremely important. Question number 13. In the early part of the 20th century, Rutherford made the first observation of an element being changed into a different element. Alpha particles were fired at nitrogen atoms. The nuclear equation for this reaction is given. Calculate the minimum energy required for the reaction to take place. So let's do that. So we need to calculate the energy that for the reaction to take place. Okay? So we're basically kind of finding... Okay, let's find the mass on both sides first. Okay, so we have the total mass here of the helium plus the nitrogen. So helium plus the nitrogen will give this much mass. And then what we're going to do, we're going to add the mass of the oxygen and hydrogen. And we're going to get this much mass. Notice that there is an increase in mass actually. So there is this increase in mass, which means that energy was supplied. Energy was supplied. Okay? If the mass increases, that means the energy was supplied. So what essentially you're going to do is you're going to find the change in mass. So you're going to subtract both of these numbers. And when you subtract both of these numbers, you're going to subtract this big number here. And you're going to minus it with the small number. And you're going to get the change in mass. And then you're going to take the change in mass and times it by 3 times 10 to the power of 8 squared. Okay? That will give us the energy supplied. And then you're going to have the energy supplied in joules. You're going to divide by 1.6 times 10 to the power of minus 13 and you're going to get 1.16 mega electron volts. Okay? And this is a relatively okay question for 4 marks. The question says, explain why the alpha particle must have greater energy than minimum energy for the reaction to take place. So let's say the minimum energy is 20 joules. So let's say alpha particle has 10 joules and this has 10 joules and both of them have the minimum energy. So and we supply this energy, so they have the energy to react. Okay, so they have the energy to react. Now we notice that the alpha particle has 12 joule energy. So it's going to have this 2 joule extra energy, right? The reason it has extra energy, the reason this alpha particle has extra energy is because of conservation of momentum. So let's say this is the alpha particle, this is nitrogen, this is oxygen, and this is hydrogen. So alpha particle needs to have that extra energy, right, to conserve momentum. So before collision, alpha particle has momentum P, and then the nitrogen has also momentum N. So alpha particle has a kinetic energy, and because of that it also has a momentum before the collision. Collision, or what type of reaction are we doing here? Yeah, we can say the collision is fine. Okay, before the collision, right? Now after, when the products are produced, the products must also have Ke to conserve momentum. Okay, if you have a momentum before, you must have momentum after. So after momentum will be equal to the momentum of hydrogen plus the momentum of oxygen. And remember, if you have momentum, you'll have kinetic energy, because kinetic energy is equals to P squared by 2m. If this becomes 0, this entire thing will become 0. So momentum is 0. Okay, but we know that they have kinetic energy, so the reactants and the products both have kinetic energy, so they both have momentum. Okay, so the extra energy needed is the kinetic energy of the alpha particle, which shows that the alpha particle has momentum before, and which also shows that the products have momentum after, and hence the momentum is conserved. Okay, so 1 mark here, and all of this stuff is condensed into 1 mark. Okay, so it's a theory question, so I explained it. Mostly it's like this only, they give the question. Another question here. In 2023, a small capsule of KCM-137 was lost when being transported from a mine in Western Australia. The activity was given and you have to show the decay constant. So decay constant is equals to ln2 half-life, ln2, and then half-life is 30.1 times converted into seconds. That's going to give me 7.31 times 10 to the raised power of minus 10 becquerel per second. And yeah, so this is approximately equals to that. Okay, that's the first part, very simple. The next thing they tell us, calculate the mass of KCM in a capsule. So 1 KCM, or you can try it yourself first as well. So 1 KCM is gonna be having 137 proton plus neutron times, or we can just say 137 U as the mass. 137 U mass. So we want to see, okay, that this is what 1 KCM has. So how many KCMs do we have in total? So what we can essentially do here is we can find the number of undecayed KCM atoms, right? The total number, and with this we can find the total mass, and for this we can use A is equals to lambda n. Okay, so activity we know is 19 giga is times 10 to the power of 9 divided by 7.31 times 10 to the power of minus 10. That's going to give me 2.6 times 10 to the power of 19 undecayed KCM atoms. So 2.6 times 10 to the power of 19x. Cross multiply, you will get 2.6 times 137 times, so this 2.6 times 10 to the power of 19 times 137 times 1.66 times 10 to the power of minus 27, which is U. So it's going to give me 5.91 times 10 to the power of minus 6 kg as my mass. That's going to be plugged in here. Next it says find the activity of KCM in a capsule after 2 years. So we can use the formula A is equals to A naught E minus lambda T, we know A naught is 19 times 10 to the power of 9. That's a starting. E minus, we know this value as this. We already found this out in the first part. And then 2 is 2 years. We need it in seconds. So we know that we have to times it by this number. For 2 years equals x, cross multiply. So 3.15 times 10 to the power of 7. 3.15 times 10 to the power of 7. So that's going to give you the answer. That gives you 1.81 times 10 to the power of 10 BQ. That's the answer to that. Right, this is the final part. It says the capsule was found after 14 days. Calculate the total energy release from the capsule in 14 days. Okay, so for this one, you know that the energy released for one decay, energy released for one decay is equals to 1.17 mega electron volts. I can find, so now what I have to do, what I can find is how many decays are happening in 14 days. So my question should be how many decays in 14 days. Okay. So now you would ask, why can't we use n is equals to n naught E minus lambda t, or A is equals to A naught E minus lambda t, or A is equals to lambda n? Well, the reason is quite simple. We want to see how many nuclei are left over after 14 days, right? So the time isn't here. We can't use this because there's no time. So this is wrong. We can't use this formula. Just cut that out. Now for these two, what the problem here is the half-life. Notice something. The half-life is 30 years. If our graph kind of looks like this is the graph, then going from here to here is going to be 30 years. And we're only talking about 14 days compared to 30 years, 14 days. Which means when we zoom in on this graph to 14 days, it's going to be approximately a straight line. Hence, we can say that A is equals to change in n over change in t. So we can use this formula instead of using these, because the change in time is very small, so small that we can assume that the graph is a straight line, and we can say that the activity is change in n divided by change in t. But usually we say that if we consider a bigger region, that it's dn by dt. Okay, so that's why we are going to use this formula specifically here. Okay, so we can use the activity, which is 19. Now activity won't change much, so that's why we're using this. It won't be that significant. Is equals to dash the question mark divided by 14 days, which we can say 14 days, and we know 1 day is this many seconds, so 86,400. So my total number of nuclei, the change in n, which is basically the number. So let's say you had 5, okay, and then you went to 3, okay. So the number of nuclei decay is 2, right? So that's basically this, the number of nuclei that have gone, that have, decayed. So we're getting that value, and that's 2.298 times 10 to the power of 16. Now what you could do is you could just plug it in here. So 2.298 times 10 to the power of 16, you could multiply with this. So we can get 2.298 times 10 to the power of 16 times 1.17 times. So I'm going to multiply it by 1.6 times 10 to the power of minus 13 because it's mega electron volts. And I'm going to get the answer as 4.31 times 10 to the power of 3 joules. That's the answer.